Sounds good. Okay. Yeah. Hi, everyone. So we officially will start this session. Again, a brief introduction for myself. If you just missed it, my name is Chen, and I'm a course facilitator from Deep Generative Model, the XCS 236 at Stanford. And today, the motivation for this sharing session is like in XCS 236, we covered a lot of uh, theories and mathematical like background about all the models, including like VAE, GAN, diffusion models. While I was taking the course, something I was wondering is how like all this like maximum likelihood and all different math proofs they are related to the training and production of like large language models. So I'm trying to combine these two together to see uh, to show like how these different concepts oh okay how these different math concepts are integrated in the training and like RLHF of current large language models. Yeah, and if you have any question, feel free to either send in the chat window or just like unmute yourself because when I share the screen, I might not be able to see you are raising the hands. Yeah. So hope that you are all seeing a Google Colab notebook that I'm sharing. I'll be sharing this notebook with you all after this session. And in it, it contains like all the content and also some demo codes about the algorithms and uh, yeah, basically the algorithms and the models I use to demo these concepts. Uh, for today's session, this is a brief agenda. The first one is what the motivation for this session, and I also briefly talked about it just now. Also, in language modeling, some basic model architectures and how their what is their like dependency assumptions, how do we compute the conditional probability, and how does this maximum likelihood methods lead us to the training methods of large language models. And the model pre-training continues from this part. So we use the maximum likelihood objective to train the large language model. And so this would be kind of natural and straightforward. One interesting thing I'll cover is how the large language model, somehow they learn the knowledge from the text they were trained on. So I'll share some interesting research results on this aspect. And for supervised fine-tuning, from a like likelihood and the maximum likelihood objective perspective, it's not that much different from pre-training. So I'll just maybe show some examples. And in the end, like for the modern large language model, for them to work very well, the RLHF step or contrastive learning, uh, they are quite essential. So I'll talk about the RLHF methods and sorry, in fact, it will be about PPO and DPO. So PPO is proximal policy optimization and DPO is direct performance optimization. Okay, if that sounds good, we'll get started. Yeah, some motivation of it is from XCS 236. We covered quite some theories about distributions, about likelihoods, like KL divergence. And suddenly, somehow we have these fancy models like transformers, GPT, and RLHF. Like, what kind of role does a transformer play in these math concepts we learned from the course? So that's why I want to connect the dots. And to start with, I'll start with a recap on the conditional probability. So because large language model, although it's large, but it's still a language model. And by language model, it's used to estimate the distribution of words or sequence of words. So the very basic idea for language model is given an input sentence, how likely this sentence actually occurs in this language. So it's actually a probability model. And in XCS 236, we also mentioned that all the generative models, no matter it's language generation or image generation, in the deep down to the bottom, there are some sort of probability models that estimate the likelihood of a given sample. So for language, we kind of very naturally have this autoregressive nature, like every new token depends on the context of the previous tokens. So, for example, the likelihood of the whole sentence, "I love machine learning," it could be written out using the conditional probability rule to be the likelihood of token I times the conditional probability of token love, depending on I, and we recursively doing so, and we write it out in an autoregressive fashion. And that is kind of a lot of language model is doing. So given the prefix, given the prompts, given the context, we use the language model to predict the probability of next token. And in this math formula, we have a parameter theta. Theta is the parameter here to model the distribution of next token. And in the current world where deep learning is so popular, theta is usually referred to as the parameters in the neural network. But sometimes just keep this in mind, and sometimes it might be easier for you to think about it. But this data could be anything. It doesn't have to be the parameters in a neural network. It could be as simple as a lookup table, as we'll see in the n-gram model. So the n-gram model is like a very simple language models before neural networks come out. And here I'm showing a simplified case, which is bigram model. By bigram model, it means for every next token, we only rely on the token before it to predict the next token. So the likelihood is expanded out instead of like instead of expanding out and every token depends on all previous tokens, writing it out very perfectly using conditional probability. Instead, we make this Markov assumption, and the whole sequence of probability is the first token times the probability of the second token, depending on the first token. Yeah, I believe you probably already tried implementing this or learned this from all different places. So the theta here, instead of a neural network, it could be just a Python dictionary. So this is an implementation, a very basic implementation of a bigram model. You could see we have a probability table here and also an n-gram counts. They are basically used to map the token to given a prefix token, like if it's today, and it lists out the probability of all different tokens would be if they are to follow the token today. And this is a very basic language model. And if we can run this and train the model. Yeah, let's give it a try. Hopefully it's not taking too long to set up. Okay, well, we can also just take a look at the example here. So I'm here after training the model, I ask it to evaluate the probability of dog given word the. So how likely it is that the pair the dog would occur, and how likely it is if the cat would appear. And yeah, it seems the dog has slightly higher probability than the cat. Um, yeah, this is a brief sample here, and we can also make a trigram model, which means every token depends on the previous two tokens, and we have a probability table to show the results. In this case, in this implementation, I don't have a fallback strategy, which means if the prefix like the cute, it has never appears in the training data, then the probability will be 0. So that's why like the cute dog and the cute cat, the probability given are both 0 because they have never been seen in the data. But the n-gram models here, just want to give you an idea of this conditional probability, this autoregressive nature, and the parameter used to model the distributions here. They are not necessarily some complicated networks. They could be as simple as a lookup table as here implemented in the n-gram model. And now we get to something modern transformer. Well, it's not actually that modern. I believe transformer paper was out 2017. But basically it will be much powerful than the n-gram model. And theoretically, one key difference is that for if we use transformer to model language, we don't have to make this Markov assumption that every token only depends on one token before it or two tokens before it, but instead the transformer takes it can see all the inputs before a specific token and give the prediction for next token. Uh, sorry. Here, well, one thing that we actually can make things a little more precise is that the theta in this probability model, if you, for example, from the course XCS 236, we kind of learned this that if we have a lot of different we have a lot of different possible inputs like x1, x1, x2, x1, x2, x3, and we want to model the distribution based on all different inputs, then doesn't that mean like this theta, this distribution, the parameters used to model the distribution needs to have enough parameters to cover all sorts of different distributions given an infinite number of combinations of x1 to xn. But a key thing here is the theta we express in this probability measure here, they are actually not exactly the parameters of the transformers. So this is something that took me a while to kind of realize. Theta is the parameters to model the distributions of next token. So it is actually, for example, it could be as simple as the mean and variance in a Gaussian distribution, or in this case, when we sample the tokens, theta is actually the logits that's output from the final layer of transformer. So for theta, the dimension is pretty much fixed. It's correlated to the number of tokens in the vocabulary. But the parameters in the transformer, they are used to take x1 to xn as inputs and output theta for all these different cases. So an example is, for example, we have
Chang, Alex is Ozzy here. I'm so sorry to interrupt you. Is it okay to interrupt, or should we wait until the end?
Yeah, for sure. Feel free to ask it right now.
Okay, so So theta is not the parameters of the neural network, meaning that theta is not the weights of the model.
That's right. So theta here is not the weights of the model.
Okay, so how do the weights of the model, as we, whatever kind of neural network we're using,
Mm,
transformers or LSTMs or whatever, how do the weights then relate to theta? Because
right,
all
right.
these models, as I understand them, once you train them, it's the weights that are sort of the pot of gold that GPT has and whatever, and then you would use to fine tune or what have you. So can you explain how the weights relate to theta?
Definitely, definitely. So actually what happens is the transformer or all other types of neural networks we have, they are used to uh, produce the data. So the process happens, I kind of put them here. So we have this input sequence from X1 to Xn. And in transformer, we have the encoder and decoder. So for the encoder, it processes X1 to Xn, produces this output features for every input token. And the decoder, we have the cross attention in transformer. It takes like all the encoded results of the given sequence and autoregressively, the decoder only looks at all the tokens that have been output so far and produces this data that we can use to directly model the likelihood, to model the distribution of next token. So theta, the parameters to define the likelihood is actually just the logits output from last layer of decoder. And we can use it directly to sample next tokens. And instead of what the transformer does, it learns to how to take all the previous inputs, all the current like existing outputs, and use them to predict the distribution of next token.
Oh,
So
sorry. So theta then is the output layer of the network, the
yes,
logits. So
yes,
and in the case of language models, it would be the logits that would then be fed into a softmax. Is that
yeah,
correct?
that is correct. That is correct.
Okay. All right, got it. So theta is basically the output layer logits that are then fed into a softmax that gives us probabilities that we then choose from, based on temperature or what have
That
you,
is correct.
to get the next token. Did I get that right?
Yes, yes, exactly, exactly.
Okay.
Um, yeah. So when we are using the large language model, a lot of times we think of it as, well, I just give it some input and it will just pop out the next output, the next token continuously. But actually, as you mentioned, there's a sampling process. So the transformer, what it gives us is a distribution of the likelihood of the next token. So if we look at it here, the next token, it might be I, it might be cat, it might be today, it might be sunny. It could be all different words, and all different words has different likelihoods. So for example, if I'm saying I like the cat. So if I say I like it is more likely the next token is cat, but it is also possible the next token is dog, or the next token is today. So the transformer or the large language model, um, if we think of transformer as a lookup table, we are not using it to uh, look up the probability of next token directly. Instead, transformer is used to generate the lookup table. Um, yeah, so yeah, to kind of, if we go back to the idea of lookup table, the reason why we had the Markov assumption that every token only depends on one previous token or two previous tokens is because if we don't have the Markov assumption, the lookup table is intractable. It's infinitively large. If we want to know what's the probability of cat, we need to define the whole lookup table, listing out all possible prefixes, and then for every possible prefix, we look at the probability of cat as next token. But what we do with neural networks and transformer here is we compress this lookup table into the weights of the transformer of the neural network. And we use the neural network to produce a lookup table in the form of the softmax output. Then we get a probability table of every token, which is a finite table that we can use to easily sample the next word, or evaluate the likelihood of next word.
Got it. So again, the output layer basically gives us probabilities, and we treat those we treat those lodges as essentially, okay, here are some possible choices or the most likely choices. However, whatever the dimensions of our output layer are, let's say they're 10. And you say, okay, here are 10 the 10 most probable choices. You pick, and then we can have different regimes for which ones we pick.
Right, right.
Okay, thank you.
Yeah, no problem. Yeah, so that's kind of how, like, from in a sense, transformer and the n-gram models, they are all pretty similar. They are autoregressive, but instead of using a fixed lookup table to track the probability of next token, we have transformer, which can take a longer input as sequence. And in the transformer, we have the attention mechanism where the probability of next word can adaptively take the previous tokens into consideration. And this is like a kind of simple implementation of transformer. And we have the positional encoding to tell the model like whether the word is the first token in the sequence, whether it's the second token in the sequence, or third token in the sequence, because this order in language, they do matter. They affect the meaning of the sentence. And I'm kind of cheating a little bit here because I just directly import the PyTorch transformer model instead of implementing all the attention has and feed-forward network itself. Yeah, as you can see, during the sampling process, the model takes the input and takes the input sequence and also the prefix of current output sequence and produce the likelihoods of all tokens as next token. And here we are doing this greedy sampling. We always choose the token with the most likelihood as next token and append it to the generated sequence. But to the bottom of this, it's still like the autoregressive model. It's still like the conditional dependency that one token depends on all the previous tokens, and it's trained with as a language model, is trained with maximum likelihood method. Well, yeah, it's actually doing the training for 10 epochs. And yeah, all the input sequence here, they are already the IDs of the tokens, so we don't see the words exactly. But here, as you can imagine, the generated sequence is not very high quality. Like there are a lot of repetitive tokens here. Yeah, and based on transformer, there have been a lot of variations. So as you may know, like the current large language models, they are decoder only. So if we look at the transformer here, we have an encoder part that sees the whole input. So a good example would be translation. We have an input sentence in English, and let's say we want to translate it into French. The encoder will look at the whole English sequence, produce an embedding, and we use the decoder to auto-regressively output the French token when we do the translation. So the difference is the encoder sees everything all at once and produce the embedding, but decoder, it still sees all the prefix, but it is run in an autoregressive way to generate next token. And one variation would be BERT. So BERT has actually also been quite popular in the NLP world before GPT and decoder-only large language models came out. It did help a lot in a lot of NLP tasks like text summarization, or like sense classification. And one interesting thing with BERT is that it is no longer, during the training of BERT, it's no longer autoregressive. It does not have this autoregressive dependency saying that given all the prefix, we try to maximize the likelihood of the model when it predicts the next token. So instead, the training method is called masked language model, or MLM. What it does is, given the sequence from x1 to xn, one of the token is masked, so it's replaced with a mask, and BERT is trained to maximize the likelihood on this masked token. So because BERT is an encoder-only model, it sees like for the whole sequence, if it's like I like machine learning and the word like is masked, BERT will see the whole sequence before the masked word and also after the masked word to predict for this word, like what's the likelihood? Is it more likely that I like machine learning? Is it I love machine learning? Or is it I hate machine learning? And it produces likelihoods to put into this possible token. There's also another training task when BERT was pre-trained called next sentence prediction. So to highly describe it, it means given two sentences concatenated together, like x1 to xn and y1 to yn, they are concatenated together with this separator token. BERT model was trained to maximize the likelihood to predict whether this first sequence it is or this second sequence y1 to yn, they naturally follow the sequence x1 to xn. So they in the training data, we might have a lot of paragraphs. We sample two sentences from it. If they are naturally one after another, then the model should return one for that kind of case. But if it's some mixed sentences with random orders, and should return false for this prediction. So you may notice that BERT is not trained for generation, because like this masked ML task, it is not used to keep appending new tokens to the end of it, but instead just predicting one word of it. This whole process of MLM training and next sentence prediction, they are used to train all the intermediate layers of BERT to know how to understand language better, to know what tokens matter most in a sentence that the encoder attention weight should pay more attention to. But during the actual application of BERT, usually there will be an application layer that will be trained or fine-tuned based on this pre-trained BERT. So we leverage BERT as it's kind of like leveraging it as an embedding model to tell us what this sentence is about. If we want to produce some summarization of it, we can use the embedding, or if we want to classify whether this is a hazardous content, we can use the BERT embedding to deal with that. Yeah, so yeah, like I said, BERT has been quite popular to do all the traditional natural language tasks, and this is also an example for running it. I just loaded a pre-trained BERT model instead of implementing from scratch. And yeah, the example task I use here is to classify the report to whether it's positive sense or whether it's negative sense. So we can see that the model, the BERT model output gives us an output. And I believe right, I believe I take for BERT, we only take the embedding of the first token of it. So usually it's a special token, and the embedding of BERT on this token will be used to do the downstream classification and prediction task. Yep. So that's about BERT. Let me see. And BERT is an encoder only model, but right now, like all the new large language models, they are decoder only. And again, there's some recap here for the transformer. We have encoder that looks at the whole input sequence, and a decoder to auto-regressively generate next token. But for the decoder-only transformer model, it sees the whole prefix, and we don't produce special encoding or special embedding for like the input sequence, but instead we just leverage the decoder to use the attention mechanism to look at the prefix and produce the probability of next token. So I say in a sense, the decoder-only model, it's somehow more like the traditional language modeling in terms of dependency. Like we only have one set of weights, parameter weights, to look at previous tokens. It's kind of like the n-gram lookup table. But for traditional transformer, the input sequence part, we have a subset of the encoder weights to handle that, and a decoder weights to do the generation. But for decoder only, it's the same weights. And yeah, I guess what is shown from all this ChatGPT and large language models is that decoder only models, they are good at generation, at producing the next tokens. But at the same time, when the model is large enough, apparently they are also good at like extracting the knowledge or even some more abstract knowledge from the text it has seen. And yeah, here I'm using the MetaLlama 1B as an example to run here. And the good thing is MetaLlama 1B, it's small enough that you can also run it in the Colab notebook. Let me see if yeah, we can probably run the demo here. Okay. This. Yeah, if we look at the sample output I have in this cell, so the whole prompt is translate the following English text to French. And I give it, hello, how are you? An answer. So this is the output of the model. Like generally, this is kind of some experience we now get from running ChatGPT. Like we have all the prompt, and the model just continues the generation, gives like the answer is bonjour, comment allez-vous, or comment vas-tu, and it also explains like the translation is blah blah blah. So this is kind of one caveat of generative model. It just wants to keep generating stuffs. I believe like if you play with ChatGPT, the modern models are getting better now, but for smaller models, um, unlike like traditional transformer-based encoder-decoder model to do sequence-to-sequence like translation, the decoder-only generative model, it just wants to keep generating the um, next token. And we need to do all sorts of prompt engineering like this with the colon, with the new line breaker to force the model to answer it. And that's also what the instruction fine-tuning stage is doing in the large language models, or else the language model will just be predicting next token. They just want to continue writing the prompt you give it to them instead of answering the questions. So the instruction fine-tuning stage is used uh, to train the model so that they answer the questions instead of just continue writing whatever prompt we give them. Yeah, the model pre-training, I think I'll skip this part. We kind of briefly mentioned it, the large language model pre-training.
Chen, sorry, going back to
Yeah.
what you were just talking about, instruction fine-tuning, where you insert a new line and answer. Um, just curious, like in GPT, that's not hard coded into the model that if you see something like a new line or answer, then stop talking and answer. That's also learned by the model. How does it know that if you insert a new line symbol and answer, that now I'm supposed to answer and not be verbose?
Uh,
Does that
uh,
make sense?
so I guess your question is, how does it know, like, if we assume that GPT is not fine-tuned to this kind of inputs, like given an answer, it starts to answer instead of continue writing, how does it adapt to this behavior?
Well, I guess I'm asking for instruction fine-tuning.
Yeah.
That's also learned. It's not somehow hard-coded into the model. In other words, you were saying that some of these decoder-only models have a tendency to keep on wanting to generate text. So how does it know that when you insert a new line and answer, presumably it's knowing that, look, I have to stop just
Mm,
generating and provide a more succinct answer? Is that what happens? And if that's what happens, how does it know to do that?
um, that's a good question. In fact, probably this is the format they use to do the instruction fine-tuning. So it's possible that on ChatGPT, it's well wrapped. When we do the dialogue, when we do the conversation, we don't see a very ugly prompt saying an answer and the ChatGPT starts answering. But maybe when the inference actually happens on the server, they do have this to separate the question from the user and also the expected answer from the model. So
See.
it's possible that during the instruction fine-tuning of GPT or other large language models, they also see things like this. It's just that on the user layer, this kind of
Abstracted away.
sorry, I didn't catch that.
Abstracted away. We just don't
Yes.
see.
Yeah,
Um,
exactly.
so what they're doing is if I ask GPT, which I just did yesterday, please explain the Frobenius norm and its use in machine learning, right?
Mhm.
That on the server, it inserted \n answer to the end of my question,
Mhm.
and that it had been trained on \n answer Okay, I see.
Yes,
Interesting. Okay.
yes. So actually, in this case, the model I'm using is Llama Instruct. So technically, this model has also been instruction fine-tuned.
Right.
But as a matter of fact, if I don't add this final new line and answer, if the prompt is something like this, um, the output would also be continued writing instead of answering the translation request. So I asked it to translate the sentence from English to French, and then the model just keeps going. It's a simple sentence with a few words that blah, 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 instead of doing the translation. So that's why even for this instruction fine-tuned model, I do append this to trigger the model to do the answer. It's
Got it.
possible that if it's a bigger model, it might do better, but um, like for instruction fine-tuning, there might still be separators like this to hint the model start the answering now.
Okay. Thank you.
Yeah, sounds good. I'll skip the pre-training part. You can play with it and look at it. One interesting thing about the knowledge from pre-training, there's some interesting research results from Alan Drew. He's a researcher at Meta, and I do find it very fun. Like it's called physics of large language models. I shared some of the results he found about the question whether the large language model really learned the knowledge, or does large language model just memorize the most possible next tokens given the previous tokens? Does it actually have the concept of abstract knowledge? And he did some experiments using GPT-2, which is a smaller decoder-only model, using bio and Q&A dataset. So it is a dataset containing the biography of a lot of different celebrities, politicians, different peoples, and a Q&A dataset to do the testing. So kind of anecdotally, some of the results, they are pretty fun, but you're welcome to read the papers. For example, like the first two results he found out is the model, if it's only trained on the knowledge, well, if it's trained with both knowledge and the Q&A tasks, the model can effectively learn the knowledge. But instead, if the model is only pre-trained to word by word memorize the knowledge, but the model has never seen a question answering type of thing, the model will never be able to extract the knowledge. So that's something quite interesting I found. So if the model has only seen the descriptions from biography, but the model have never seen data about question answering, then if you ask the model any question, the model will never be able to extract the knowledge and answer your questions correctly. And some intuition for result 3 is that if we want the model to learn the knowledge, to learn the abstract concepts of the knowledge, it will be helpful to have all different sorts of augmentations, like permutations, repetitions. So an example here, the experiment is also quite impressive. So if the model has only seen the biography of each person only once, then the Q&A accuracy is only 9.7%. It's really low, 10%. But if there are some augmentations added to this biography, like for every person, the biography, we reorder the sentences, we do some paraphrasing, and for each person, we have 5 different biography texts. We use it to pre-train the GPT-2 model. Then the QA accuracy would be boosted from less than 10% to 96.6%. So it kind of means that the large language model needs to see the same content in all different formats so that it could decouple the language itself and the knowledge. So some other types of augmentations might also include translation. So if the same knowledge is expressed in different languages, in English, in French, in German, the large language model would know, let's say if the knowledge is United States is in North America. If the model only sees it in English, then the model might think, I don't know what United States is. I don't know what North America is, but I just know United States usually precedes the occurrence of North America. But if the same thing is written in different ways, in different languages, then the language model might know that the abstract concept of United States is related to the concept of North America. So yeah, something I found quite interesting. Another thing is that bidirectional models like BERT is much worse at learning knowledge. And the hypothesis Alan gave is that for bidirectional model like BERT, because it's so powerful, it sees all the information before the masked token and after the masked token, it became lazy at memorizing the knowledge. Yeah, so again, these are more like from me, it sounds like some anecdotes, but you're encouraged to please read the paper, which I find very interesting. And yeah, we only have 10 minutes left. I'll skip the supervised fine-tune and multimodal part. And I do want to talk about the RLHF, the reinforcement learning with human feedback, which is very important in the training of large language models right now. So the first method proposed is proximal policy optimization. It's used in GPT-4 to tune the model to give higher quality results. The reason is that if we are just doing supervised fine-tuning with the maximum likelihood method, well, either it's the pre-training part where we give it a large amount of corpus and we ask the model to predict next token, or even if we do instruction fine-tuning by providing a prompt and we train the model to predict the tokens in the answer, it still has its limitations. One thing is the data collection could be very expensive. So imagine we're doing instruction fine-tuning, we would need to ask the vendors to provide data by answering questions like, please implement PPO algorithm for me in Python, because these are some questions that people will ask GPT-4 and we want GPT-4 to do well in. To actually collect data to do supervised fine-tuning like this, it will be quite expensive. And a second reason is that if we, no matter it's pre-training or supervised fine-tuning, is maximum likelihood, trying to maximize the likelihood of the given the whole corpus by predicting the most likely next token. But this might not be what we really want. So there's a misalignment between the maximum likelihood optimization and human preference. Just like the translation case with meta model, it is predicting the next token with most likelihood, but it's not helping me with solving my translation request. So on the other hand, it's cheaper to just identify, to give a preference, like showing two results and people choose which one is easier, which answer is better. This is both easy for human and models. So this is the kind of basis why we can train the model to give rewards. We can train a reward model to help us in this reinforcement learning loop. So the likelihood we are going to optimize here instead of the maximum likelihood optimization, we're trying to maximize the likelihood of given an input X. This X might be the prompt. We want to maximize the likelihood, and if we know that, for example, the answer Y1 is better than the answer Y2, we want our model to give the answer Y1 a higher likelihood during generation. So here we can have a reward model. The reward model tells us, given the prompt X, how good, like how much reward we can get by by answering it with y1, and how much reward we can get from it by answering with y2. And with this maximum likelihood method, we can first train the reward model. And in the end, the actual large language model we want to optimize is this pi model. We want to find the pi theta that could maximize the expected reward given all the possible prompt x and the response y sampled from our large language model pi theta. We want to maximize the expected reward, or you can also call it return. We want to maximize the return. But to train our large language model based on this it's not likely, but based on this objective, based on this maximum return objective, there's a problem with it. That's because notice that we have an operation here. We sample y from the large language model. We sample the responses from our large language model, and we calculate the rewards. But this sampling operation, it is not differentiable in large language model. We have basically after softmax, we either do the argmax operation to pick the most likely word, or if we have temperature, if we do beam search, then but greedily we just do a argmax, and this argmax operation is not differentiable, which means we cannot calculate, we cannot just directly maximize the likelihood of this expected reward function and optimize our large language model policy pi. And that's why reinforcement learning came into the picture. So a recap here about reinforcement learning. Reinforcement learning has been quite popular, especially when AlphaGo, AlphaZero came out. Reinforcement learning really impressed the world about how much it can achieve. But reinforcement learning here came to help because with the reinforcement learning method, it's okay that our policy pi or our large language model, the output is discrete. So it's kind of like in Go or in other games, the actions are also discrete, whether to move up or move down or where to place the Go stone, I guess, if it's called stone. And we use reinforcement learning method so that there is a way to leverage the rewards, and we can still update the weights in the policy in the large language model, even if we cannot do a direct back propagation from the reward into the policy. We can use reinforcement learning to connect them, to bridge them, and we can still update the policy. Yes, so there are some more details here. Oh, I see Vasil raised
Yeah.
the hand.
Yeah, I have a question in terms of rewards. If you scroll above, you have a reward statement as customer account preference data. So, like user itself, after, for example, receiving answer from LLM model, setting does it satisfied by answer, or like how we initially getting the reward in terms of scale, like from answer from 0 to 1?
Yeah, that's a good question. So the reward model here, it is trained with human annotated preference. So that's why it's called
Okay.
human feedback. We collect the human feedback first to train this reward model. The reward model itself, usually it's also initialized with a pre-trained large language model, because the pre-trained large language model is very capable at understanding the language. But usually people add a final linear layer to it to take the output of the final decoder, and instead of predicting the next token, we run the regression to give a reward based on the inputs. And the likelihood when we train the reward model is this one here.
Okay.
Yeah.
Makes sense.
So
Thank you.
yeah, no problem. Yeah, and the whole process of this proximal policy optimization, it is actually a very widely used algorithm in reinforcement learning, not only for large language models, but you can also use it for gaming, for robot control, all different kinds of reinforcement learning. The problem with it is that to bridge this, to mitigate this gap that we cannot back propagate the reward into the policy gradient, what happens is during the model training, we first sample the outputs from the model. Then we run the reward model to grade these samples, and then we use the graded rewards to do model updates. So the whole process, there are some complications in it. For one thing, we have two models, the reward model and the policy model. The reward model has to be separately trained with human feedback, and the reward model, if the policy model is updated too much, then the reward model might also need to be refreshed so that it can provide more informative response. So this whole iterative process of sampling, grading, then do model updates, sampling, grading, then do model updates, it is a little more complicated, and that's why a second algorithm called direct preference optimization is proposed. The interesting thing here is that the reward model is removed from the picture, and instead the reward model is replaced mathematically in the expression. We can replace the reward model by expressing it in terms of our policy function itself. So in this case, it means when we calculate the reward, we only need our policy model, our large language model. And when we want to maximize the this likelihood, we want our model to give the right preference. We don't have to do the sampling, grading, and then update. We can directly update the gradients through with back propagation. We can back propagate the neg log likelihood loss into our large language models, and we can run the updates. Yeah, that's so that would be all kind of there are some sample codes here to about DPO and also about PPO. The PPO, the proximal policy optimization demo code here is using Gymnasium, so it's not large language model. It's actually a little game called card pull. You move the card to make sure the pole always stand on top of it, and so you can see like through the training, the rewards the model keeps increasing. The model is getting better at stabilizing the pole. So yeah, that says it's interesting to look at, but we're out of time. Try to stay a few more minutes to answer a few questions, but yeah, I'll share the notebook so you can also play with it. And feel free to drop out if you have like other matters to attend to. Yeah, Alex, let's go ahead.
Hi, sorry for being such a hog with your time. A couple of questions. If you can go back up to the very beginning of the notebook where you did the positional encoding.
Yeah, it's this one.
Right. So I've never quite understood how you use the sine and cosines to encode positions. I understand that you use sine and cosine to code repetition, but I don't understand. I've never quite understood how it helps in positional encoding. So if you can explain that, that would be great.
Yeah, for sure. So the positional encoding, the repetition of sine and cosine is kind of not the key here, I'd say. Like sine and cosine, they are periodic functions. But if you look at their cycle. The cycle, for example, in transformer, I believe the cycle is 10,000 or something like that. So this means that when we embed the index with sine and cosine, we can we will really not see repetitive values on positional encoding. So that's the first thing, because we don't want the positional encoding to repeat itself after, let's say, 10,000 tokens. Then it means the first token will get the same positional encoding as the 10,001 token. That's something we don't want. We want it to be always different for different positions. And that is achieved through this cycle of an integer, actually cycle of an irrational number. I guess the cycle is 10,000 pi or something like that. So the encoding is never repeated. And at the same time, because at different position, we get different values out of sine and cosine. So that's how we have different values for the tokens at different position, and that's the way like the position information is passed into the model. And one reason for choosing sine and cosine is, although we are not trying to make our positional encoding periodic, but we do make it always oscillating between -1 and 1. So that the positional encoding from its scale, it will not affect our model. Like the position is not linearly increasing or decreasing in any way. In that case, the model would get confused. Like the whole input will have a shifting norm in this encoding, but instead with sine and cosine, the norm will always be between 0 and 1, yet we get non-repetitive encodings for all different positions.
Okay, great. Thank you. And then the second part of my question was when you spoke about the example with persons' biographies and the ability of the model to retain knowledge if the same biography was presented with different wording, I guess, from the same information was presented in different ways, essentially.
Yeah.
Right. Now, the study that you mentioned was just purely for training. I assume that the same would apply for in-context learning. That these days when we do work with GPT or whatever for in-context questions and providing context, that the assumption would be that there would be benefit in sort of stating the same context 2 or 3 different ways. And the thing, presumably it should apply, right?
Yeah, this I'm not sure. So the in context, you mean we provide the context in the prompt, and
In the prompt, exactly, yes.
Yeah, if we mutate, like change the wordings of the context multiple times, then probably the large language model could better answer our questions and leverage the information from the context better. And in this way, I'm a little not sure. Is one difference is during pre-training, we are updating the weights of the model. So the knowledge, or basically the abstract relationship between these tokens, will be baked into the model. But in the context, or well, it's not exactly few-shot learning, but by providing the information in the context, it's just during the runtime, we have more information for the model to look at. So it's not about extracting internal knowledge from the large language model. It is also not like instilling new knowledge to the model. So it would be an interesting study to see by changing and presenting different forms of the context, if it's beneficial, is it really because it helps the language model to understand it better, or simply because if it's longer, then it has a larger ratio in the whole prompt, and the model is more likely to pay attention to some of the information in the context.
Interesting thing to study, though.
Yeah. Yeah, that's right.
Great, thank you.
Okay, I guess that would be all. I see some questions in the chat, but seems that they have been answered by the audience. Yeah, so if that's all, we can probably end it here. And I'll share the notebook. You can also reach out to me with the Stanford email address.
Thank you very much, Cheng. This was really, really great.
Thank you,
for your
Alex.
session. It was a great session.
Thanks. Yeah, I'm glad you enjoyed it. Okay. Yeah, end it here, and see you in the future.
Okay.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you.
Bye.